Welcome to this video on intermolecular forces and states of matter. We will explore how forces between molecules affect the physical forms that matter takes. Intermolecular forces are the attractive or repulsive forces between molecules. They include dipole-dipole interactions, hydrogen bonding, and London dispersion forces. These forces are crucial in determining a substance's physical properties. Dipole-dipole interactions occur between polar molecules. Their strength is proportional to the molecule's polarity. While weaker than ionic or covalent bonds, they are stronger than London forces. Hydrogen bonding is a special, strong case of dipole-dipole interaction. It happens when a hydrogen atom bonded to nitrogen, oxygen, or fluorine interacts with another highly electronegative atom like N, O, or F. London dispersion forces are the weakest intermolecular forces present in all molecules. They are caused by temporary fluctuations in electron distribution, and their strength increases with molecular size. Liquids have a defined volume, but an undefined shape. Key properties of liquids influenced by intermolecular forces include surface tension, capillary action, viscosity, and vapor pressure. Surface tension results from cohesive forces at a liquid surface, making it behave like an elastic membrane. This property allows things like water striders to walk on water and is affected by temperature. Capillary action is the rise of liquids in narrow tubes against gravity, a balance between adhesive and cohesive forces. This is vital for water transport in plants and applications like paper towels. Viscosity measures a liquid's resistance to flow and is influenced by intermolecular forces and temperature. Examples range from honey's high viscosity to water's low viscosity. Vapor pressure is the pressure exerted by vapor in equilibrium with its liquid phase. It increases with temperature and is related to boiling point and evaporation rate. Phase transitions are changes between the states of matter, such as melting, vaporization, and sublimation. These processes involve the transfer of energy, being either endothermic or exothermic. A heating curve graphically displays temperature versus heat added. The plateaus on the curve indicate phase changes, where latent heat is absorbed or released without a temperature increase. Phase diagrams illustrate a substance's stable phases under varying conditions of pressure and temperature. Key features include phase boundaries, the triple point, and the critical point. The triple point is where solid, liquid, and gas phases coexist in equilibrium. The critical point is the temperature and pressure above which distinct liquid and gas phases cease to exist. The solid state has a defined shape and volume, with molecules in fixed positions. Solids are categorized into crystalline solids, which have long-range order, and amorphous solids, which do not. Crystalline solids have a regular, repeating 3D structure and a sharp melting point. Amorphous solids lack long-range order, resulting in a gradual softening instead of a definite melting point. This image displays examples of ionic solids, such as iron 2, sulfide, calcium bromide, and sodium chloride. Here we see examples of molecular solids, including nitrogen, ice, and dry ice. These are held together by intermolecular forces. This slide illustrates network covalent solids like diamond, silica, and silicon, characterized by their extensive covalent bonding networks. The final category of solids shown are metallic solids, exemplified by platinum, brass, and nickel. Crystalline solids are built from a repeating unit called the unit cell. Common lattice types include simple cubic, body-centered cubic, and face-centered cubic, which determine the solid's properties. The simple cubic structure has atoms at the corners of the cube and a coordination number of 6. This is the least efficient packing of the cubic structures. The body-centered cubic, or BCC structure, has atoms at the corners and 1 in the center, giving it a coordination number of 8. It exhibits more efficient packing than the simple cubic structure. The face-centered cubic, or FCC, structure has atoms at the corners and in the center of each face. With a coordination number of 12, it represents the most efficient packing of the 3 cubic structures. In summary, intermolecular forces govern matter's behavior, influencing liquid properties, phase transitions, and solid-state structures. Understanding these concepts is essential for materials, science, and chemistry.